Uh, in general, a force in the same direction, like F1 below of motion, we say it does positive work. A force opposite to motion, like F2, does negative work. But here's the problem, Cody. I've told you that work is a scalar. How the heck can direction be showing up when I've told you that direction doesn't matter? So I wrote here, although work can be positive or negative, it's not a vector. It has no direction, much like your future. So what does negative work mean? We're going to talk about what negative work means today. We're going to talk about energy. The definition of energy, Lean, energy is the ability to do work. In other words, if an object has energy, it can apply a force over a distance. There are many types of energy. One common one is the energy of motion. We call this kinetic energy, but I'm going to abbreviate that for the rest of high school as capital K, capital E. There's my abbreviation for kinetic energy. Heat is a form of energy. Heat is usually created by friction. This next one has two words, gravitational potential. First of all, underneath the word potential, you can just write the word stored. Any type of stored energy is called potential energy. So in a battery, there's electric potential energy, stored electric energy. In a slingshot, there's stored elastic energy, elastic potential energy. So gravitational potential energy, Brendan, that's stored energy due to an object's height. Here's the word potential again. You can even draw an arrow pointing there. Chemical potential energy, that's stored energy in a chemical reaction. A good example would be gunpowder or the food that you eat for that matter. The reason you need to eat food is your bodies need energy because they need the ability to do work, and you get it from food. Many others. Sound energy, sound is a form of energy. Elastic energy, the energy you store in a rubber band, it would be elastic potential energy until you let it go. Nuclear energy, this one for what it's worth is the E equals mc squared. That E stands for energy. And it turns out if you take matter and you turn it to pure energy, the amount is the mass times the square velocity of light, which is crazy big. And a nuclear bomb, when a nuclear bomb goes off, only a tiny amount of the radioactive material is actually turned into pure energy. I think it's on the order of about 0.5%, but that alone is enough to make that huge explosion. So in this course, we're going to look at what's called mechanical energy, which is broken down into two main types. Kinetic, PE, and potential. Usually it'll be gravitational potential, but not always. And the concept of energy, Lauren, explains negative work. When you do negative work on an object, what that really means is that the object is losing energy. I'll pause the video. Potential energy is, what word did I use to describe potential energy? Started with the letter S. Stored energy. There are many ways to store energy. A great example is if you're using a bow and arrow. When you're pulling the bow, you're storing energy in the system. Suppose it takes, oh, I like example one, I like example one. Example one is a nice question. Oh, you know what? It might not be on a test, but it'll be on a quiz. So suppose it takes 250 newtons of force to pull the arrow back 0.78 meters. Davin, what's A asking me to find? How many what of energy? We did work. I'm going to start out by saying work equals force times distance because energy is the ability to do work. Did I apply a force? How big? Was it applied over a distance? Double check, were the force and the distance in the same direction? I pulled it that way. The distance was that way. Yep, so we can use this. What do you got? Sorry? 195? Anybody else? Yeah. Carson, you can use a calculator for that one if you need to. Okay? That's how much energy, Brendan, we stored in this system. When you release the string, what happens to all of that stored energy? What does it get turned into? What form? Yeah. Turns into Ke. Put the phone away. Face down. This is your conscience speaking. I'm not even moving my lips. Okay. I have a great example of this. Put your pencils down, look up. I have fun. Have we applied a force over a distance? Have we done work? Yes. Have we stored energy in this system? What type of energy? Elastic. When we let this girl go, what will the energy get transformed into? Cody, very kinetic. Ready? Three. Lean, this is good. Look up. In some ways, that looks kind of cool. That one, I don't know if I would try. The fact that she was upright, I'd be very concerned about whiplash or injuring my back. But there is a resort, I think it's in Minnesota, that does offer this. You're in a horizontal position, you're wearing a neck brace and helmets and pads, which you should. Then I think I'd be willing to try it. You may have seen something similar at some theme parks. I've seen it in Florida. There's a ride that you get in where you're basically sitting in a giant ball, a life-size ball, and it's hanging from bungees, and they winch you down to the ground, and then they let you go, and you bounce up and down like a giant yo-yo really quickly. That one I'd be willing to try as well. Very, very similar physics. Storing potential energy, turning it into kinetic. It's good physics. When you stretch a rubber band, you're storing elastic potential energy. I think we're turning the page. A battery has stored electric potential energy, but in this unit, we're primarily going to be looking at one specific type. We're going to be mostly looking at gravitational potential energy. This is the work that you have to do against gravity in order to change an object's height. And I think we can figure out the equation. So potential energy due to gravity is mgh. Or if you know Fg in newtons, it's just Fg times h. That's what we did in our thought puzzle at the very beginning of this class. Jaden has a mass of 75 kilograms. What's his weight? Isn't his weight 75 kilograms? No! How do I find weight? Who remembers? No, now. Yeah. Yeah, weight is mg, not mass. So, in fact, weight is a synonym for Fg. It's going to be mg. It's going to be 75 times 9.8. What is it? 735 units, newtons. Okay. On the moon, the weight would be different. Okay. When Jaden jumps, he can raise his center of mass 75 centimeters. Nice try, Dueck. 0.075 meters. I really disagree with that. 0.075 meters is about that much. 75 centimeters, I think, is about that much. I think it's just 0.75 meters. Yep. At the top of his jump, how much potential energy does he possess? Well, Jordan, you're probably fairly familiar with the potential energy equation for weird reasons. What's the equation for calculating gravitational potential energy? So it's going to be, now, you know what? I know mg. It's going to be 735 times 0.75. If I hadn't done mg already, I would have gone 75 times 9.8, but it was sitting there screaming at me, so okay. What'd you get? Surely you know if I know that you're not on your calculator, I'm coming at you, right, Zapicha? Brandon, what'd you get? 551? Isn't there a decimal or not? Sorry, 551.25? Units, it's energy. Joules. Okay. This is why, by the way, energy and work have the same units, because energy is the ability to do work. Where'd that energy come from? It's got to come from somewhere. Don't overcomplicate it. Where do you all get your energy from to do stuff? Yeah. Energy came from PE in food, not gravitational PE, chemical potential energy stored in food. This is why, by the way, if I just made you, for some unfathomable reason, jump up and down in one spot, you will get tired fairly quick, because your body has a certain amount of energy that it's stored. It'll start to go through that. What happens when you burn through the available energy? What does your body do? No. Okay. Then it starts to work on fat. That's why all of us store body fat. That's a safety procedure that our bodies have developed, so that if you're in a situation where it's do or die and there's no food, you don't die. You'll lose weight. So is also why if you do really, really heavy exercise, you can lose weight. You don't see too many, long distance runners that are packing a lot of pounds. They're generally thin. This is meant to be Captain Obvious. How much gravitational potential energy does an object have if it's on the ground? Exactly as a number in your head, Carson. What's its height if it's on the ground? So what's its potential energy if it's on the ground? Fair enough? Okay. Second type of energy, kinetic energy. This is the energy of motion. You know what? We had so much fun deriving the last equation. Maybe let's see if we can figure out how to derive this one. I'm going to hit Ke equals a half mv squared. V what? Cooper, V what? V what? Say it again, you're right. That square dominates your life in ways you don't realize. I can explain an awful lot about riding bikes and stuff from that. I can explain an awful lot about car accidents from that. It dominates your life. Oh, and if you're an athlete, it dominates your life as well. 357 Magnum bullet weighs 8.1 grams. Nice try, Dueck. How many kilograms is 8.1 grams? Kilo is going to be divided by 1,000. It's going to be 0.0081 kilograms, and it travels at 490 meters per second. I like those units. How much kinetic energy does it possess? Well, Ke equals a half mv squared. How do I type 1/2 on my calculator? What's the easy way to type it? 0.5 is the quickest. M.0081. I looked it up. That's the numbers. V, I looked that up as well and converted it. 490. Don't forget the squared. How much kinetic energy does a fairly powerful bullet have? More specific as a number exactly. Brandon picked up the hint because he knew I was coming at him soon. Ashton, what'd you get? 9604? Yeah, I don't think you're going to get in the thousands. That'd be a fair chunk. I think it's in the hundreds, just under 1,000, isn't it? Cooper, what'd you get? 972? Is that right? Point what? I'll go to 3 sig figs and I'll just say, yeah, I know a heavy bullet, because I'm a nerd, I've just memorized a few things. I know a heavy bullet has about 1,000 joules, just under 1,000. Could be a bit more, could be less. Okay. I told you that squared explains a lot. A car has a mass of 1,000 kilograms. How much kinetic energy is required to reach a speed of 5 meters per second? Well, let's crunch the numbers. What's it asking us to find, Jada? Ke equals a half mv squared. It's going to be 0.5 times 1,000 times 5 squared. What do you get, Jada? I have no idea what you're saying. 12,500? Anybody else? Okay. How many times faster are we going in part B, Jada, than in part A? If now we're going 10, we were originally going 5. How many times faster is that? Twice as fast? Are we going to use twice the energy? Let's find out. You should be able to just backspace and change the 5 to a 10, right? And don't forget the squared. You don't get twice as fast. I think you're going to get 49,000? Is that what it is? 50,000 on the dot? And if you go 50,000 divided by 12,500, if you go 50,000 divided by 12,500, Anderson, you notice something. What is it? Twice as fast as 4 times? What do you think 3 times as fast is going to be? Not 8 times. No. Give you a hint. Think about that squared. Nope. What's 3 squared? It's going to be 9 times more energy. What if you're going 4 times as fast? 16 times more energy. Let's convince ourselves of that. Let's actually crunch the numbers. So 15 is 3 times faster than 5. If you backspace and edit on your calculator, whoops, didn't want to hit that, Mr. Dueck. Okay. If you go 0.5 times 1,000 times 15 squared, what do you get? I think it's 112,500. Yeah. I didn't do this math in my head. I multiplied the 12,500 times 9. And if you divide 112,500 by that, make sure I'm still recording, Mr. Dueck, good, by 12,500, you get 9, yeah? Okay? So let's generalize this. Suppose an object has a kinetic energy of 5,000 joules. How much kinetic energy is required to double its speed? Spoiler alert, not twice. It's going to be 2 squared. Or what? Can you multiply 5,000 times 4? Yep. What if we triple its speed? What are we going to multiply by? Not by 3. So it's going to be 5,000 times 9. Yeah. Can you crunch that, please? 45,000? 16 times 4 squared. Okay, it's the square of the amount because it's a half mv what? Squared. That's why I was picking on Cooper and having him repeat the squared. It's going to be 5,000 times 16. Which I'm pretty sure is 80,000, but double check me. So this explains, first of all, the last 20 years, the big revolution in sports equipment, especially where you're using something to strike something else, golf clubs, tennis rackets, hockey sticks, they become lighter, not heavier. Now, Jordan, what was the equation for kinetic energy that we derived from you? Ke equals, loud and proud, you're right. Now, when m gets smaller, that's less energy, but when you make it lighter, you can swing it faster. That v squared more than makes up for the trade-off. The tennis rackets that I played with when I was a kid, man, they feel like they're made out of lead when I pick up a modern tennis racket. And boy, can I generate racket head speed. And boy, that v squared kicks into effect. Hockey sticks, same idea. The only exception, baseball bats, that weight, you're required to have that weight in the major leagues or in little league. They don't let you muck around with that very much, so that hasn't changed. But man, most of the other sports, golf is the really big one. Especially if you look at your grandfather's or your grandmother's golf set, if you're a golfer, it'll feel like you're swinging sledgehammers around. You can't get anything with them. We've made everything lighter. It's a bit of a trade-off because there is an m in the equation, not an m squared. We made more than make up for it by being able to swing it faster, and you get more bang for your buck. So in golf, for example, we always talk about club head speed. If you watch a golf match, they'll say, oh, look at the tremendous club head speed that pro generated. This explains why it's more difficult to speed up once you already have some kinetic energy. If you're riding your bike, to go from 0 to 5, that's a 5 meter per second increase, not much work. But to go from 5 to 10, which is the same 5 meter per second increase, that squared's kicking in, it's going to take you way more work. You're going to be doing more work per second, more power, more time. Oh, you want to go from 10 to 15? Still the same 5 meter per second increase? You're really going to have to be pushing it. This also explains why in a car you can't just hold the gas pedal down and keep going faster and faster and faster and faster and faster and faster. Eventually, whatever energy that engine is putting out, you're using all of it up. And now I got to get serious. This explains why damage to the occupants in a car accident is so dramatically different between an accident at, say, 20 kilometers per hour versus a car accident at 80 kilometers per hour. The people in the 80 kilometer per hour car crash will experience how many times more damage? Not 4. And now I'm about to explain about 90% of the car accidents out there. If you're going 4 times faster, how much more distance will it take you to stop? Not 4 times the distance. What? That right there explains a lot of car accidents. People don't realize. You're going twice as fast, it's going to take you 4 times further to stop. Oh, you're going 3 times as fast, it's going to take you 9 times further to stop. Oh, I'm a good driver. No, you can't argue with the physics. Don't give me the good driver BS. So my message to all of you as a teacher who does love all of you, slow down. Don't drive stupid. Say that again.
If someone's slower than you, faster, and you both stop,
Who's in front?
the person's first.
Okay. Yeah, it'll take you longer. So
So
what
you're
if you're a good driver, you always make sure you leave enough distance that you can do a panic stop between you and the car in front of you. Most people don't. Then you're asking for trouble. Yeah. I like example seven. I like example seven. Example seven is a nice question. Evelyn, what's example seven asking me to find? Yeah, now I'm going to go V equals question mark. Do you see a VI or a VF or a T or an A or a D anywhere in this question? No. Do you see momentum in this question? Because all of those had V's in them as well. No, in fact, I see KE. Yes? Let's write, I think that would pivot me to the kinetic energy equation. Can you read me the kinetic energy equation, please, kiddo? I wrote it a little bit differently. I wrote it as mv squared over 2 for a reason, because I'm going to rearrange it. Oh, Cody, do I need to put the 1 for the 1/2, or does the 1 make a difference at all? So I didn't bother writing it. What are we trying to get by itself? How would I move the m over? Divide it. How would I move the 2 over? That's on the bottom. Times it. And that's going to give me this. V squared equals 2 ke over m. V what? Squared. Oh, how does one get rid of a squared? One wonders. Yes. If you really feel you want to, you can add that to your green sheet. You know what I would say? If we were doing the test, I would say hold off until the day before the test. We might, the reason I'm trying to get ahead is I'd like to try and give you a final quiz on this just so you can tweak your grade and bump it up a little bit. So if you want to add this to your green sheet, but I think it's something you can learn to derive as well. It's going to be the square root of 2 times 924.5 divided by 25. Evelyn, what'd you get? I have no idea what the answer is here. Might work out nice though. Maybe not. 8.6 units. Yeah. You can also start to use this in roller coaster design. So suppose a roller coaster has a kinetic energy of 137,200 joules at the bottom of the first hill. First question, how fast is it traveling? Okay, we can handle this. Cooper, what's A asking me to find? So I would say to myself, I'm probably going to think V equals. I don't see a VI, a VF, a T, an A. I don't see a momentum. You know what? I see kinetic energy, so I would jump straight to that. Cooper, can you read to me the kinetic energy equation? KE equals. No, read me the equation from the formula sheet. I chose to write it as mv squared over 2 because that's easier to get the v by itself. That one just gets in the way. Cooper, how would I get the v by itself? What I'm going to do with the m? What am I going to do with the 2 that's on the bottom? By timesing it. So it's going to be 2 times the kinetic energy divided by m. That's going to equal v squared. V what? How'd I get rid of squared? In fact, Evelyn just derived it with us. It's going to be 2 times 137, 200. I'm missing a 7, Mr. Dueck. Divided by 350. This might work out nice, but maybe not. Cooper, let me know what you get. People are saying 28. I don't know. Yeah. Do me a favor. Can you convert that to kilometers per hour? Is it times by 3.6 or divide? I can't remember. Sorry? How many kilometers per hour? Okay, that I'll line up for an hour for that. I don't think I'll line up for 3 hours for that. I've been on faster. I'm a coaster nut, by the way. I love roller coasters. So I've been on faster, but that's pretty good. That's like being on the freeway in a convertible. Okay, I'll line up for that for a while. Gonna make it lean? Okay. Suppose you want people to be traveling at 28 meters per second at the bottom of the first hill. How high do you need to make the top hill? Here's what we're going to say. Potential energy is mgh, but here's the nice thing. I know how much potential energy there was exactly because they told me all of that kinetic came from potential. Carson, how much kinetic was there in A? Yeah, it's going to be 100, what was it? 130, 137, 200? That equals mgh. Nathan, what do they want me to find? Get the h by itself. And now we're getting into ride design. This is how we can calculate or design a roller coaster ride. Yep. Apparently the height is going to be the kinetic the energy that we want at the bottom of the hill, and we can figure that out by figuring out how fast we want to be going at the bottom of the hill. Work your way backwards. How high does the first hill need to be? Now, this is assuming we're not losing anything to friction. In real life, you are losing a little bit to friction. Although they grease those roller coasters down pretty good. What do you get? Sorry? 4-0? Okay. Pretty high coaster. I've been on better, but I've definitely been on worse. How high would we need to lift an object to give it a potential energy of 15,288 joules? Okay. Anderson, what's this asking me to find? And I see potential energy. You know what? I think we're going to use PE equals mgh. What do we want to get by itself? How? Dividing by PE? Thank you. I think the height is going to be the potential energy divided by the weight. If I was really lazy. So it's going to be 15,288 divided by 65 times 9.8. Like you needed that. Sorry, how much? 24. Anybody else? Yeah? Now that you know the potential energy, if it all turns into kinetic, could you figure out how fast it was hitting the ground? Yep. So we use this in industry. For example, let's suppose you might recall when you were kids, they were pile driving by the Golden Years Bridge for a couple of years, driving large, large beams into the Fraser River. So suppose you want a 2,500 kilogram pile driver and you've worked out the numbers, it has to hit the ground at 18 meters per second. Well, first question, how much kinetic energy does it need? Lauren, how can I find kinetic energy? And I'm hoping you're looking at your green sheet and realizing where we are. That's why I'm doing all this, so that your eyes will start to subconsciously glance in the right location. So it's going to be 0.5 times 2,500 times 18. Don't forget the squared. I get 405,000. Double check me. Yeah. So that's how much energy it has to have at the bottom. Well, if all of that energy comes from potential energy, how high do we need to raise it? Okay, Jordan, coming back to you. What's this asking me to find? Part B. Sorry? Can you, which equation are we going to use to find height? Do me a favor, without writing it out, get the h by itself. Give me that version. H equals something over something. Is that okay? Are we comfortable going straight to that step since the original's on your formula sheet? Yeah, it's going to be my answer from A. You can use your answer button. Divided by, and I'll have to put the bottom in brackets, 2,500 times 9.8. I don't think this will work out evenly. Even? 16 point what? 0.53. Okay, so 16.5. Okay. So let's suppose you're the engineer, you've calculated this, and then Cody, you go out to the work site and you realize there's a tree growing right where the crane needs to be, where the pile driver needs to be, and that tree has a branch sticking out, and unfortunately that branch is 12 meters off the ground. It's in the way, and the ministry won't let you cut it down. Does that mean you can't do anything? What do? The answer is you say, I guess I need to increase the mass. I need to get a bigger pile driver because there's also an M in that equation. I can make right? If I make the mass bigger, I don't need to lift it as high to get the same oomph when I get to get the same 405,000 joules. So it won't hit the ground as fast, but it'll still pack the same energy. So you would go back to your numbers. You would say, okay, if this is how much energy that I need, what's the highest height I can get? I can only get 12 meters high. Okay, how big a pile driver do I need? So we can use this. One more, we're done. A person is running at 7 meters per second. If they have a kinetic energy of 1764, what's their mass? Oh, okay. Carson, what are they asking me to find here? And what did they give me? Yeah, because I've also found mass using F equals what M. You know what? Look at the kinetic energy equation. Do me a favor. Get the M by itself. V squared. Or you could write it, if you let instead of a 0.5, if you let it just be a 2 on the bottom, it's also twice the KE divided by V squared. I don't care which version you use. Let's be bold. It's last block and I've been talking for a while. Go straight to your calculator without writing out the numbers, see if you can get an answer. I think I tried to make this work out evenly. $72?
Yeah.
Anyone else? Yep. Units, it's a mass. Kilograms. What's your homework? 1 is good. You're going to get time to work on this tomorrow, so this is not due tomorrow. You'll probably get about, ideally, half an hour or so. 2 is good. 3 is good. 4 is good. 5 is good. These are mostly plug and chug. In fact, I'll even say if you can do it without writing anything down, check your answer. The answer's right at the back. I'm okay with that. 6 is good. 7 is good. 8 is good. Skip 9. 10 is good. Skip 11. 12 is good. Skip 13. 14 is good. 15 is good. Skip 16. Sorry? I think there is a 1-6. Yep. 17 is good. But you can work on a lot of this tomorrow.